Calculus is the first time in a math class that we really get to work on optimization, that idea of picking the best input to give us the output that we want the most. So what production level should I have at my factory if I want to maximize the profit? Or what production level do I want at my factory if I want to minimize the cost? So here's an example from the beginning of chapter 4 in your book. What if you had a function that told you, given how fast you drive your car, so given the velocity at which you drive, v, what gas mileage do you get? We might want to use that function to figure out what speed we should drive at to get the best possible gas mileage. Calculus can help us do that. Your clue that this is an optimization problem is that word best. So best is a superlative word. So best, greatest, longest, shortest, fastest, furthest, richest, poorest, brightest, dimmest. These kinds of words are superlative. And when you see a superlative word in a calculus problem, I want you to start to think optimization. So we could try to solve that problem from the beginning of chapter 4 by using a graph. Remember, this along the input axis is the velocity at which you drive your car, and the outputs are the gas mileage that you get, and we want the highest possible gas mileage. We can look at this graph and see we are interested to know what is going on right there, because whatever velocity I drive at there, that's giving me the highest possible gas mileage, and that's what I want. So we're looking for the output value, the gas mileage, and we're looking for the input value that gives us that best possible gas mileage. And again, we can use calculus to help us find that out. The key to optimization problems is remembering that theorem from 4.2 or 4.1 that didn't even really have a name. It just said that if there's going to be a maximum value, a relative maximum or an absolute maximum of a function, there are only 3 possible places that we even have to look, that we even have to consider. The maximum can happen at an endpoint, or it can happen at a local extreme value, and those only occur at critical points. So I have to check endpoints, I have to check places where f prime equals 0, and I have to check places where f prime is undefined. Frequently you'll find on the AP test that they write the questions because they, in a way that doesn't prevent you from making the common error of not checking the endpoints. So we're going to have to check endpoints, and we're going to have to check critical values when we're looking for maximum values, minimum values. Those are going to be our answers to optimization problems. I printed these 7 steps here for you. 7 steps might seem like a lot of steps for a problem, but I think you'll get the hang of it. It won't feel like 7 steps, but we do want to make sure that we cover all of these bases when we are trying to solve an optimization problem. So I'm going to go through the first example, and then we'll come back to this list, so we'll have something a context to talk about. Okay, so this is an example multiple choice problem that was actually published in 1998. We're asked to find the maximum acceleration attained on the interval times between 0 and 3 inclusive by a particle whose velocity is given by t cubed minus 3t squared plus 12t plus 4. So I've sort of numbered these steps in order of the 7 steps that I've given you. Our very first job here, number 1, is to recognize that this is an optimization problem. They weren't very subtle about it. They've in fact even used the word maximum. So that should be pretty obvious. We're looking for the maximum acceleration. So step 1 is to decide that I'm trying to maximize acceleration. Step 2 is to come up with a formula, a function for acceleration. Well, I wasn't given acceleration, I was given velocity, but I remember from chapter 3 that to find a formula for acceleration, given velocity, I can take a derivative. So I'll write my formula for acceleration as 3t squared minus 6t plus 12. My third step, so I know I'm going to maximize acceleration. I need the critical points of acceleration. To find critical points, I'm going to have to find the derivative acceleration and find out where that is either undefined or equal to 0. So I'm going to set a prime of t equal to 0. I get one solution. That's at time equals 1. And I do have to remember, it doesn't happen to matter here, I also need to check any place where a prime of t would be undefined. But a prime of t, 6t minus 6, is linear. Linear functions, there's nothing about a linear function that could be undefined. I don't have a 0 in the denominator. I'm not trying to take the logarithm of a negative number or of 0. And I have no radicals that I could be trying to take the square root of a negative number. Okay, so step 4, I've got my critical point. I am ready to make my table of values. So here I go. Into my table of values goes any endpoint. I was given endpoints of time 0 and time 3, and any critical points. I only found one critical point, so he's going to go in my table. Time equals 1. My next step is to actually evaluate values of the acceleration function. These are the only these places in this t-chart are the only places I have to look. I'm guaranteed that my maximum is the result of plugging in one of these 3 values. So I'm going to plug in 0 for time. Remember, I'm maximizing acceleration, so I'm going to plug into my acceleration function. I'll fill in my table. So I've plugged in all the possible locations for the absolute maximum, 0, 1, and 3. I found 3 possible accelerations, and the maximum is going to be the one that is the biggest. So I would say that the maximum acceleration on the intervals 0 to 3 is 21.